In this video here, we're going to take a look at the center of mass of a set of particles arranged in a plane. What we're now going to do here is build on what we introduced in the previous video to find the center of mass of a set of particles that are now arranged in a plane. And to do this here then, we're going to use these two relationships, or these two results here. Now, these two results here, we established these in the previous video, right, when we were looking at particles lying along a straight line. So this result here, don't forget then, this result here, it's when the particles lie along the x-axis. Let me make a quick note here. So that's for the x-axis here. And then this result here, this is when the particles lie along the y-axis. And again, let's just make a quick note here. So clearly you should recognize these two results here. If you don't, just go back to the video, watch the previous video, and then come back to this video here. So like we said, then we're going to use these two results here to find the center of mass of a set of point masses arranged in a plane by considering the x-coordinate and the y-coordinate of the center of mass separately. However, there is a quick way to do this, and that is to use position vectors. So if we have a system that consists of n particles where mass m1 has position vector r1, mass m2 has position vector r2, mass mn has position vector, and you might have guessed it by now, right, rn, then in that case, we obtain this result here. So the summation here of mi times ri from I equals 1 to n is equal to this here. So we have r bar, which never sounds correct when I say it, but r bar times by this summation here of ri from I equals 1 to n. And r bar here is just the position vector of the center of mass of the system. And as you can see here then, this result is very, very similar to what we had here then for the x-axis and the y-axis. The only difference here now is we're using ri and r bar, okay? Obviously, because we're now working with position vectors, okay? Just know here as well then, that if the question does not specify axes or coordinates, you will need to choose your own axes and origin, okay? So please be aware of that. For some questions, they won't give you the axes or coordinates, and it is important then that you do choose your own axes and origin. So in terms of an introduction there to the center of mass of a set of particles arranged in a plane, there isn't really too much more to go over here, right? Again, very similar to the previous video. This is essentially kind of like laying the foundations and the fundamentals here to, further centers of masses. There we go. I can't speak. And again, it is all very straightforward. So I don't want to go into too much detail here for the introduction. More than anything, this is the key result here. So please do make a note of this. This is really, really important. So please note this result. But other than that, you don't need too much more, right? I think the best way to really demonstrate this is just work through. So for this video, we're going to work through two practice questions. Okay, so let's not waste any more time then, and let's just get started with question 1. So let's just get started then with question 1 here. And what we have then for this question is a system of 3 particles that consists of 5 kg placed at -1, 1, 3 kg placed at 2, 3, and 2 kg placed at 4, -2. And all we want to do here then is to find the coordinates of the center of mass of the system. And again, just as we saw with the previous video and question 1 with that video, I say question 1, there was just the one question for that video, but again, this is a pretty straightforward question, okay? So where do we begin here? Well, we just need to make use then of our standard result here. So we're going to use then the summation here of mi times ri, where ri here is our position vector, and this is equal to then. So what we get here is r bar, that never sounds correct, so r bar here times by the summation then of mi, okay? Using this result here then, we can easily find r bar, right? R bar here gives us the coordinates of the center of mass of the system, okay? So what we get here then, on the left-hand side, and I'll just do that over here then. So what I'm going to get here is 5 times by -1, 1. We'll then add that to 3 times 2, 3, plus 2 times 4, -2. So let's just put it all together then. We get 5 times -1, 1. We then get 3 times by 2, 3. 2, 3 like that. And then finally 2 times 4, -2. So 2 times 4, -2. Perfect. So this here gives us the left-hand side here. And this will be equal to them. So what we get here is the sum of the masses. So that's 5 plus 3 plus 2. So 5 plus 3 plus 2, like so. And then we times this by r bar. So at this point here, we don't know what r bar is, right? We just take that as x bar and y bar, like so. Okay. So let's just start by simplifying the left-hand side here. So just expand right by the scales on the outside here. So I get minus 5, 5 there. So minus 5, 5. I then get 6, 9. So we get 6, 9 here. And then finally we get 8 minus 4. So 8 minus 4, like so. So that's the left-hand side there. Again, I'll just simplify that in just a moment. Let's just deal with the right-hand side as well here. So the only thing that we can do here then is just simplify this bracket, right? So 5 plus 3 is 8, plus 2, that gives us 10. So we get 10 lots here then of x bar and y bar. So x bar, y bar there, like so. So let's just simplify the left-hand side here. So I've got minus 5 plus 6 plus 8. So 14 minus 5, that gives me 9. So we get 9 there. And then 5 plus 9 is 14, minus 4, that gives us 10. So we get this column vector here, 9, 10. And that is equal to 10 lots then of x bar, y bar. So x bar, y bar. Okay? And all we want here then is x bar, y bar. I can't speak anymore. So that's all we want here, right? So x bar, y bar. Too many bars. So to do that, or to obtain this here, all we need to do then is just divide by this coefficient here, 10, right? So therefore then, what we get here is x bar and y bar. And that is equal to then, so 9 divided by 10, that would give us, that would give us 0.9 here. And then 10 divided by 10, that would just give us 1. Perfect. So in that case then, to finish with here, the center of mass. So the center of mass here is, and my coordinates here then are 0.9 and 1. So like we just said, then we get 0.9 and 1. And there we go. So hopefully not too challenging there, but that gives us the solution to question 1. And then finally, to finish with here, we have the very last question for this video, question 2. Now for this question, what I've got here is a light rectangular plate, ABCD, which has AB measured at 30 centimeters and AD measured at 50 centimeters. We're then told that the plate has particles of masses 3 kg, 1 kg, 2 kg, and 2 kg again attached to the plate at these points here, so A, B, C, and D respectively. Now for this question then, all we want to do here is just find the distance of the center of mass of the loaded plate from the following axes. Now as we can see then for this question and this problem here, we do not have a diagram, right? And generally speaking, for most further mechanics 2 problems and questions, we do really want a diagram. So a good starting point here is to just draw our own diagram, okay? Now it doesn't matter if your art skills are as bad as mine, we are just simply drawing a rectangular plate here, so it should hopefully be pretty straightforward. So what I've got here then is A. We also have B. We'll also have C. And we'll also have D. So if we join this all up together then, this will form our rectangular plate. Okay. And we'll get something that looks like this, right? And what I'll also do here is just mark down then the particles here in a different color, just so they kind of stand out a little bit more, right? Perfect. Okay. Now, before we can do anything else, what I need to do here is choose one of these points or these particles here as my origin. Okay. So what I'm going to do here is choose A as the origin. I'm going to choose A as the origin. Choose A as the origin. like so. What I'm also going to do here at the same time as well is choose AB and AD to be our axes, right? So we choose A as the origin and AB and AD as axes. Okay, perfect. So what I also want here is the coordinates for each individual point or particle here and also the respective masses. So if A is the origin, then A is just simply 0, 0. That's just 0, 0, right? Now what about B? Well, AB is 30 centimeters. So the X coordinate here would just be 30 and the Y coordinate here will be 0. Perfect. What about C then? So for C here, we have 30 units along, or 30 centimeters along here, and then the Y coordinate here will be 50, right? So that's going to be 30, 50. We get 30, 50 there. And then finally for D here, well, that would just be 0, 50, right? So 0, 50 there. Perfect. And then finally, what I also want here is the respective masses. So it's 3, 1, 2, 2 along the rectangle here, right? So 3 kg, 1 kg, 2 kg. I'll do it over here. 2 kg. And then finally, 2 kg. Perfect. And I think at this point here, that gives everything that we need then for our diagram. If we are missing anything, then we can just clearly come back to this at a later stage. But for now, I think this here is perfect. Okay. What we also need to do here is use the result that we mentioned and established in the beginning of this video, right? So let's just make a note here. So we will use them. So we will use the following result here. So we have then the summation of mi, that is the mass of the ith particle, times by the position vector of the ith particle, like so. And this here then is equal to r bar times by the summation of the masses here, right, of the particles, like so. Okay. And this result here then will give us what we need. So for the left-hand side here, basically all we're doing here then is taking the mass of the particle and timing it by its coordinates. So what we get here then is the following. We get 3 times by 0, 0. So what I'm going to do here is just take the coordinates and present those as not position vectors, as column vectors. It just makes my life a little bit easier here for the calculations. We get 3 times 0, 0, just like that. I then have 1 times 30, 0. So 1 times 30, 0. Now clearly, I don't really need to kind of bother writing down the 1. Sorry, I can't speak. I don't really need to bother writing down the 1 here, but we just do it anyway. Or I'm going to do it anyway just for the sake of completeness. But in your exam, feel free to kind of just omit that as you go. For the next one here, that's 2 times 30, 50. So 2 times 30, 50. And then finally here, we have 2 times 0, 50. So 2 times 0, 50. Perfect. Okay. So this here is the left-hand side of this result. We now need the right-hand side here. So for the right-hand side then, let's just begin by summing the masses here. So what do we get then? So I get 3 plus 1 plus 2 plus 2, right? So 3 plus 1 plus 2 plus 2. And what we do here then is we times this by r bar, right? And r bar here is just simply x bar, y bar, okay? As a column vector. So x bar and y bar. Perfect, okay? So let's just simplify the left-hand side here. So 3 times 0, 0 is just simply 0, 0. Again, in your exam, you probably wouldn't bother writing this down, but I'm just going to write it here just so you can see my full working. 1 times 30, 0 is just simply 30, 0. I get 30, 0 there. I've then got 2 times 30, 50. So that is 60, 100. So 60, 100 there. And then finally, 2 times 0, 50 is 0, 100. So plus 0, 100. And that is equal to then, so we just simplify the right-hand side here. 3 plus 1 plus 2 plus 2. That just gives us 8 here. So we get 8 times x bar, y bar. Okay. So again, one more time here, let's just simplify the left-hand side then. So 0 plus 30 plus 60 plus 0 is just 90. 0 plus 0 plus 100 plus 100 is 200. So what we've got here then is 8 times x bar, y bar is equal to, what did we say then? So we said 90 and 200 here, right? So 90 and 200 here, just like so. And then finally, we want x bar and y bar here. We just divide by 8, right, on both sides here. And therefore then, x bar and y bar here is equal to, so 90 over 8 then is the same as 45 over 4. We get 45 over 4, and then 200 over 8 is the same as 100 over 4, which is just simply 25, right? And there we go then. So we're pretty much done here. To finish with them, let's just state then the distance of the center of mass of the loaded plate from AD and then finally AB here. So for A then, I mean, this question here, you kind of do all of the work in as like a prerequisite almost. You know, at this point here now, A and B, we just simply answer looking at x bar and y bar here. So x bar then would give us the answer to A here. So that would give us the distance of the center of mass of the loaded plate from AD. So COM, just meaning center of mass, from AD. So the center of mass from AD is equal to 45 over 4 centimeters. So don't forget the units here. We are working in centimeters. So 45 over 4 centimeters. Perfect. And then finally for part B here, you might have guessed it by now, right? So for the center of mass then from AB, that is just simply y bar, right? So the center of mass then from AB is 25 centimeters. Perfect. And there we go then. So this here is the solution to part A. This here is a solution to part B. And there we go then. So that gives us the solution to the very last question here, question 2. And that brings us to the end then of this video here on the center of mass of a set of particles arranged in a plane.